For some reason my camera is not working today, but that's all right. We got the rest of it up and running. Bless. All right, so I think last time you guys were working on 323, and now next one up is 330. I pushed off deadline for homework till Tuesday so that we have a chance to look at like the next few problems. We'll probably get through at least 330 today, maybe start 34. We'll see how it goes, see what we're up to. Sound good? All right. So for this question, we have like a lunar rover. So we're on the moon trying to drive over a hill. And we want to drive as fast as we can, but we don't actually want to leave the hill, like not like launch off of the moon. So the question is like, how fast can we move? And to get started, what do you think you could do first that would help kind of work through this problem? How would we get started here? Yeah.
Draw a picture.
Draw a picture? Yeah. What kind of picture do you want to draw?
Like of the hill.
Of the hill? All right, I like that. All right, so we got like hill, got a rover. Maybe we're on the moon, so maybe some craters, right? He's got some crazy underwear on, Martian underwear. Cool. So we're driving up and over a moon. Yeah.
Do you think maybe a free body diagram might help?
Free body diagram. All right. So for free body diagram, do we need to consider like rotation of the rover? Like, does it matter if we're going up and over a hill and we're trying to figure out max speed before we leave the ground? Do we care about rotational inertia? Yep.
I think if you were to get to the point where it's facing the most upward, if that makes sense on the curve, that might be good, because then that would mean the speed or the, I guess, acceleration of the rover would be the most upward, which is it would need to overcome the gravity downwards, I assume.
Okay.
To leave
Yeah.
the surface, something like that.
Okay. Something like that. So what is that one? Yeah. Okay. Yeah, centripetal acceleration. Makes sense. I mean, we have like some kind of constant radius, right? Constant speed, constant radius. Something about a centripetal acceleration. Like usually that's when centripetal acceleration gets introduced, right? So how do we tie all these concepts together into a free body diagram? Do we need a full do we need to consider like changes in angular momentum? Or can we say that this is a point mass moving along a curve? Point mass is always easier, right? But is it enough information to get started? You can always try it, right? You can try. So we'll try a point mass, right? See if it gets us anywhere. Then if we're talking about like centripetal acceleration, that's going to fall into our kinetic diagram. And like, it's not the end of the world to like put kinetic diagram terms like you can technically centripetal acceleration can be a centrifugal force over in your free body diagram. But the only thing that usually people run into problems with is that acceleration gets double counted. Like you end up with like two MA terms, like in the kinetic diagram and the free body. So it's better to just, every time you're talking about acceleration, put it in that kinetic diagram, at least to start. And then once you have an equation, you can do whatever you want with it. All right, so what does that free body diagram look like?
I guess the normal force, yeah, it was up there with the dots.
Yeah.
I'm trying to think. Is pushing back from the ground.
Okay. Yeah. Yeah, because we know like we're trying to get over the hill at a constant speed. So when we're going up, we need gas. When we're going down, we need brake. Yeah. Yeah, you can say that it's some kind of driving force. Oh, I see. So n bigger than n. Yeah, that's right. Okay. I mean, that was for the free body diagram. Yeah. If n is bigger than mt, then oh, yeah. All right. Good luck. Yeah. Yeah.
I'm trying to think if there's like a force that was, I would call it force that pushes it forward the bars.
Yeah, so someone else was just talking about that too. It's like going up the hill, we gas, and down, we need brake. Yeah. So like one thing you can do is sort of normal to the path is like you're driving force. And at the end of the day, you're going to get friction because your tires still reduce whatever friction pushes back.
So the top of the other just
Yeah. All right, so at least if I'm thinking about like, hey, this is my normal force, I can say like normal force is kind of normal to the hill. Meanwhile, gravity is kind of trying to pull me back down the hill somehow, or at least just pull me through the Earth, through the moon Earth. And then there was a question about like, well, if we're going at a constant speed, then what's the force creating that constant speed? That's a really great question to think about, because if somebody gives you, if you have a constraint of like, I need to move this thing at a constant speed, you've implicitly assigned a force that force is going to be there and create that speed no matter what. So one way we can kind of take care of that is that it's going to be always tangent to the curve, but some kind of driving force. At the end of the day, like it's dominated by whatever friction I have. Like if it's steel tires on ice, then I can only accelerate to whatever, like 0.2 of a g or something. But big rubber tires on deep sand, like I can get a lot of like pushing force. It uses a lot of power, like there's a lot of rolling resistance, but I can get a lot of force out of it. Cool. Did anybody else come up with other forces you were? What? Oh, you think drag?
Yeah, but I don't know how the density is.
On the moon?
Oh, it's on the moon?
It's the moon, yeah, because it's a lunar rover. I mean, technically, it doesn't say lunar rover, but it does say G is 1.6. So if G is 1.6, I guess it could be like in a pool. Like maybe we're testing this lunar rover in a pool going over a hill. Yeah.
There be friction?
Friction? So friction, when you're driving, the only thing pushing you forward, the only external force is friction. So that driving force is like mu times, some kind of mu times n. At least that's our max driving force. But this is where it gets confusing. There's a rolling resistance, which has the exact same formula as friction, but that one opposes rolling. So if you want, you could say there's also this thing that's like a rolling resistance. The only difference is when you go to look up the table of values of like, here are my two materials, instead of looking up static friction, look up rolling resistance. And now you've got a way to say how much power you need or whatever, like any of those kind of questions. Cool. What about our kinetic diagram? What does that look like? Where's MA pointing? Or do we have A? Do we have an acceleration? No?
So if you're on a curve,
Yeah.
i.e. changing direction, would that
Changing direction.
count as acceleration?
So that is acceleration.
Like inward to the center.
Center seeking acceleration, something like that. Centripetal. Yeah. So we have no change in speed, but we do have change in direction. So now we've got an acceleration that's always perpendicular to that path. Something like that. Yeah, at least for this case, if we have MA, since we have V is constant, then MA is always describing like center seeking acceleration, centripetal. So what kind of coordinate system do you want to use for this.
I mean, could use either, but maybe polar might be easier for this case since
Polar?
it's a constant
Okay.
radius. So then all you have to really track is the like the theta.
Okay. Yeah, so in our like polar coordinate system, we would have a radial and a transverse direction. So if I'm saying that this is theta, E theta is describing increasing angle, ER is saying you're leaving the hill, and the center, when R is 0, you're at the center of the hill. Maybe at the alien's home, maybe he dug like a little hole down to the center, and he put a little marker to say R equals 0. And in that case, I can say AR is R double dot, which is 0, but minus R theta dot squared. A theta is like R theta double dot and 2 R dot theta dot. But theta dot is constant, so theta double dot is 0. That would be like our polar, if we want to describe it, polar.
Is that X for AR? Is that negative R?
That one's a negative R, yeah. So let's pull up where that came from. So polar coordinates, you can always look up, like acceleration is always the same definition. Once you say like, hey, I'm using polar coordinates, you always have the same definitions. Like you have R and theta describing position, and the changes in R and theta are now describing velocity, and then the changes in those changes are acceleration. So you can always look that up. Another, have you heard of inertial frame of reference? Inertial frame. I know you've used it because you were talking about centripetal acceleration. But so the inertial frame is kind of a nice frame of reference whenever you're talking about like what is the point actually experiencing, because it's always R equals 0 is the thing traveling. So you're always talking about like positions relative to what you're trying to describe. And there we have like two components of acceleration. One is a change in speed, like how fast the speed is changing. Then the other one is that centripetal acceleration, so v squared over r. So I want to write that one up too, just as like you have two options, right? And let's do some pink. I always like pink. So here I have this E normal, E tangent, oh my god, keeps popping up. So in that inertial frame, we have two components. One of them ends up being 0, same as the polar coordinates. So last step is finding like two sets of equations, Because whenever we say like this vector equals that vector, we have two sets of equations. We can break that vector into two components and say this set of components equals that set of components, right? Like the x and the x, the y and the y, or in this case, like r equals r, theta equals theta. But somehow we can split that up. So what do those equations look like as you split up those components of the free body diagram that we just drew, and then our acceleration at MA, where that one's pointing? What does that look like? Yeah, you can use either one, polar or inertial.
It's just when you pulled up this one, there was like an additional in front of.
Oh, there's also like r
Yeah,
dot
r
dot.
dot.
Yeah, I just knew that that one's 0 because r
Yeah.
is constant.
Okay, I assume so.
Yeah.
And so that's why it's not included in.
Yep. Yeah.
Okay.
How's it going? And those components. No. I mean, we can split up both of them, or you could choose. You mean which system? Like coordinate system? Yeah. I like inertial just because we're looking for speed and it's right in the thing. But they're both going to get you to the same like final answer. Right. Yeah. The only one that gets hard to use is Cartesian. My God, I'm going to stick to like x and y pointing this way and that. Yeah. Yeah, that would describe like MA is mv squared over r, like that centrifugal accelerations. Yeah. Yeah, and usually it's introduced with like constant speed kind of problems, but you can have changing speed and it's still v squared over r. That describes if you're changing direction. Yeah. Oh, because I knew that this one r is constant, so this is 0. So this should be a 2 r dot theta. And since r is constant, everywhere I saw a dot, there's a dot for r. That's why I just dropped those two terms. And that one was the other one. Yeah, exactly. Yeah. And these we have like a constant radius, or we have like a constant theta dot that terms drop out. Negative r dot squared and r. What is this one called? And r data squared. So this is a 2 and r data dot squared. Oh yeah. Where does the second term come from? So F is just going to be like N and G. Like those are the only two things that we take along that R. And then like this MY is just one time. Just so it doesn't get double counted. Yeah. No forces in there? Not sure.
Yeah, he's kind of waiting to see what's waiting, to see what he's standing outside the room. I'm not sure.
Not sure? Okay. What forces did you put?
The components are
Yeah, yeah. Okay, yeah. We don't need to like know like what the angles and stuff are, yeah. Yeah, not sure. So like as we're building equations of motion, like there's gonna be like a lot of terms that we throw in there, like especially for theta, r, x, y, like any of those like positions and velocities, we're not gonna know them. We know that the definition of position is that like it has to be at some angle. So its velocity is r theta dot. And that's okay. Like we can use those things, and then once we get to an equation, now we can start using that to like solve for things. So if I'm doing, I like the inertial frame, but do you want polar coordinates or inertial? What was your what were you going for here? What do you feel like? What like calls to you? Inertial frames? I weighted the scale though, because I said I like it. But it makes sense to me. So we'll try inertial. So along that EN direction, what's pointing along EN? MA, yep. So I can say that MAN is equal to what forces are in that N direction. What's normal to my path? Is N normal to the path? Hopefully, right? Normal force? Normal force should be normal to my path. So yeah, normal force is along that AN. Positive or negative? Is it in the direction of EN or opposite EN? Opposite. So we have a negative N. What about MG? Is NG pointing along that EN or tangent to, or a little bit of both? What? A little bit of both? Yeah. Little column A, little B. So we need a little bit of some trig, right? So if that's theta, this is theta. So I've got a plus NG cosine theta. I don't know what theta is, and right now I'm just trying to get to what are the equations that are going to help me solve this problem. That's okay. Theta is some function of time, right? Then in that now in that tangent direction, I know my MA is 0. And I can say there's like a negative mg sine theta, and then some kind of driving force minus some kind of rolling resistance. But all that stuff is just like maintaining, like how do I maintain a constant speed? And we're not trying to figure out how much power we need. We're trying to figure out max speed, just assuming that we can get as much power as we need. So equation 2, we can just say it's there, but we're not going to use it. So mv squared over r is mg cosine minus n. Do we have enough information to figure out max speed? What happens to these values if we go too fast over the hill? If we're moving 100 miles an hour after burner's on, what happens?
If you were to like leave the hill with the normal force be 0 since it's different.
Yeah, so at some point, if we're moving too fast, normal force is less than 0, which would mean that somehow there's like an anchor or a magnet or like kind of a Rick and Morty sort of sci-fi solution that's pulling the thing back down onto the hill so that it doesn't leave this lunar hill. So that's not going to happen. So what I can say is that n has to be more than or equal to 0. If it's 0, then I'm probably going to leave the hill a little bit. If it's more than 0, then I'm still safely kind of driving over the hill. So what is that, Vmax? What's our Vmax then? How do we get to that point?
I'm sorry, can you explain how you got the first equation is empty cosine theta not sine?
Which one?
The empty cosine theta minus n. Can you explain how you get to that?
Oh, how I got there?
Yeah.
This one.
The n or the negative n plus empty like you.
So I know n is pointing up that way.
So yeah, which one's n? Is this the normal force?
N is normal to the ground, so whatever keeps the rover from going through the hill. Mg is my mass times, here on the moon, it's 1.6 meter per second squared. And what I'm saying is that, like, if I'm going up the hill, that I'm at some angle off the top of the hill. So if that's my angle, then this is theta. So this component, to say like mg is a sum of a normal component and a tangent, the normal component is that mg cosine theta. So those are, and that's the only two forces that act along that, like, normal to the hill direction. It's only equal if v is 0. Yeah. So if you hit the brakes and you come to a stop, then you're definitely not going to fly off the moon because n equals mg cosine theta, and we're good. But if you're moving, if we plug in like v is 100 meters per second, like 200 miles an hour, now, yeah, we can try it. I think a 200 kilogram rover over 100 meter times, let's call it, yeah, 100 meter per second squared. And theta, I mean, it can be anything. We'll call it 1 at the top of the hill, right? So 200, or wait, 2 over 1, so 2 times 100 to the second minus 200 times 1.6. So n would be negative 19,000 newtons. So we would need 19,000 of newtons, 19,000 newtons holding us to the surface of the moon somehow, which is like probably about the size. You'd probably need an anchor that you would use for like a large 19,000, so 19 kilonewtons. Yeah, like a pretty big boat anchor to like keep you onto the moon. But you're moving pretty fast. 200 miles an hour is fast even for Earth to go over a hill. I'll actually leave it. So that's too fast. We want to go slower than that. That's more than Vmax. So what do we think Vmax is? How do we get there? Trying to get us. I'm kind of like leaving like some breadcrumbs, but I want to see how you approach it. Put in a Vmax. Yeah, you can say like plug in Vmax is something there. Yeah. Which car? What were you gonna do? Or did you have like? Oh, okay. All right. So I didn't make you lost. No. Yeah, I'm just trying to catch up.
So we have on the bus, right, where is that?
Yeah, I was trying to like plug in some numbers. Like we know how big the hill is. We know how heavy the car is. So let's say we're moving way too fast, then what would the normal force be? In this case, negative is what happens if we're moving too fast. If we're moving 0, then it's equal to mg cosine. Yeah, it's equal to mg in this case. Yeah. So we're trying to say that n will always is more than 0, which is less than.
He's probably going to be in branch. Or maybe the farming one. Because he's a county, so he doesn't have to do what
I was thinking of that test out.
I mean, 10 over there and 1, n is regular. So you could say like, all right, down to 0. Yeah. And then solve for it. That works. Yeah. That's even fast. I know it does. Because I said 100, and it was, so that's even faster than I plugged in.
I just used, I didn't know what angle to use, I just used 45 degrees. Because I figured that the y component would be the biggest. I guess that would be.
Yeah. So if you're on a hill and you're 45 degrees off the top of the hill, that's because
But I just mean like the angles.
yeah. So at the top of the hill, you're at angle 0. How do you climb? 0, right? The slope is 0 at the top of the hill. So now walk down the hill. Now I'm at angle. Now I'm at 10 degrees. Now I did 10.
Well,
So at 45 degrees, I'm at a 45 degree incline.
yeah.
Trying to get up the hill. 45 degrees steep. Yeah.
So what angles are you?
So less than 30, say a small angle. Yeah.
Oh, I'm sure that's all.
All right. So I like to check in and kind of see how people approach these. I'll show you at least like my kind of math way to keep track of less than, more than, like how this stuff kind of works. So I know n has to be more than or equal to 0. But I also know n is equal to, so I'll move that, mg cosine theta minus mv squared over r. So those are the two things. Here's like condition, or let's do it like condition A, condition B. If you're trying to like keep all your ducks in a row and keep track of things, I want to satisfy these two things. So then I can say mg cosine theta minus mv squared over r is more than or equal to 0. Since that is n, I already said, like, based on my free body diagram, this has to be true, and based on the condition that I'm not leaving the surface, then then that value has to be more than or equal to 0. So now I know, drop the m's, g cosine theta is more than or equal to v squared over r, or rg cosine theta is more than or equal to v squared. So now I've got this, like, v is less than or equal to square root What do I do with that cosine theta, though? Before I just plugged in a 1 and said I'm at the top of the hill. but it's a less than, so, I mean, cosine can go to 0, right? I'm not trying to stay above it. So what do I do with that cosine theta? Yeah.
Small angle there.
Small angle? What does that do to the hill if we say it's a small angle?
We're at the top of the village.
That we're at the top of the hill? Yeah. So let's draw a semicircle hill. Actually, I'll just draw a full circle, right? Oh, wait. Oops. Oh my God. Give me my... All right. So this is the angle that I'm walking kind of up the hill. If I'm at an 80-degree angle trying to climb a semicircular hill, how steep is the hill? Very steep. It's 80 degrees that I'm basically like walking into a vertical wall. Like because if you're 90 degrees off the top, you're walking up a vertical wall. So the hill is probably not a full 90 to 90, right? It's probably more like something like that. Even 45 to 45. Have you ever been on a 45-degree angle surface or like a hill? I've only done it one. I mean, I've been on like climbing walls, which are 90 degrees, but there I'm like actually gripping. I'm like trying to overcome the force of gravity with my hands and feet. But in terms of like walking up a surface, the only time I've been on 45 degrees was the back of Half Dome, which is, when you look back, it's like so steep it almost gives you vertigo. So most of the time, most hills, like Horse Barn Hill, it's probably never more than like 10 degrees or something in terms of like from the bottom to the top, and roughly it's all kind of constant curvature as you're going up and down. So theta is much less than 1, which means cosine theta is 1. Always nice. Small angle is like, that's our engineer. We love linear approximations. Which makes things even easier, right? Root RG. Boom. 100 times 1.6. So as long as we're moving less than that square root, root 10 times root 1.6, something like that. What do we get for that? I think I saw like 12 or 16 floating around. Did anybody plug in some numbers? 12.6 sounds right. 12.6. And the only nice part about kind of like doing it out like that is you don't end up mixing up like, was it less than or more than? Do I need to be moving faster or slower than this? Like we kind of have a step-by-step process to get there. Cool. I think we have 2 more problems. We'll try to get through those Monday. And I'll see you then. Have a great weekend. Yeah.